And since the proton is, of course, heavier than the electron, it tells us that the magnetic dipole of a proton will be around 2,000 times smaller than the one of the electron. Okay? So you just need to do that in principle. And so coming back to in the 30s, Stern, who after realizing the Stern and Gerlach experiment with his colleague Walter Gerlach, that was in Frankfurt, got a professorship position in Hamburg, which was very important, and he was professor there. And he wanted to measure, again, the magnetic measurement of the proton. So he went to his colleague, and his colleague, as also professor of theoretical physics in Hamburg, was Wolfgang Pauli. And Pauli told him, we know the magnetic moment of the proton because we know the difference in mass between the proton and the electron. And we know the electron magnetic moment. But if you like doing difficult experiments where you know the result in advance, go ahead, lose your time. And so Stern was always very impressed when you read his memories. He was very impressed by Pauli, but somehow he said, okay, he's a theoretician. I want to do the experiment. I don't care about his advice. And for that, he got Nobel Prize in 1943, which was attributed to him. And this is a citation for its contribution to the development of the molecular ray method and the discovery of the magnetic moment of the proton. So it's really for the discovery of the value of the magnetic moment of the proton that he got the Nobel Prize, not for the Stern and Gerlach experiment that is so important in the history of quantum mechanics. And I would like to describe the beauty of that experiment. So basically, Stern was a specialist about molecular ray, making a molecular ray apparatus, atomic beams. And that was what he realized with Gerlach to measure the quantization of the electronic spin. Now you want to measure the proton. But then you can say, I have a problem then, because of course, if I take a molecule like hydrogen, then I will have interaction of the electrons orbiting in the molecules that will somehow be much higher than the one that I expect from the proton itself. Because there is this difference of 2,000, 3 orders of magnitude of difference between the magnetic moment. So how, and if I have already difficulties to measure the splitting associated to the electronic dipole, magnetic dipole, how can I measure something with an accuracy that would allow me to detect the influence of the magnetic dipole associated to the proton in the molecule? But then there was already some knowledge of quantum mechanics enough to design the experiments with hydrogen. If I take the ground state of hydrogen, L equals 0, I have 2 electrons in the symmetrical combination of the orbital L equals 0. N equals 1, L equals 0. But if I want to do that, due to Pauli exclusion principle, which was already known at that time, then you need to put, following Hund's rule also, you need to put the 2 spins, sorry, into the singlet state, okay, which in chemistry you represent by this design of the molecules. You fill the orbitals, the electronic orbitals, by 2 spins in opposite directions. This corresponds to the singlet state S equals 0 in the addition of angular momentum. So the total spin of the electrons, of the 2 electrons in the molecule is S equals 0, the singlet state. Okay? So basically, the 2 spins will not, since the 2 electronic spins are antiparallel, if there is now this inhomogeneous magnetic field applying on them, then it will have no influence on the electronic cloud. That's remarkable, okay? So somehow, there's no problem. The electronic spin is in a state where somehow you do not take that into account. the homogeneous magnetic field will only be applied on the proton spin. And now you have two protons. So again, you know the angular momentum rule, and that was already known somehow in at that stage of the development of quantum mechanics. Then you have two possibilities. Now the total new angular momentum associated to the two protons that I will call capital I is equal to 0 or 1. I had two spin 1/2. I can obtain either spin 0 or total spin 0 or total spin 1. Okay? Singlet state, triplet state. So now if I apply that in a busy a magnetic field along the z-axis, I will measure the projection of m for these two values of the total angular momentum. This will be m equals 0, okay, and no influence of the inhomogeneous magnetic field. The hydrogen molecule will go straight in the apparatus. Now here I have three possibilities: m equal plus 1, m equal 0, and m equal minus 1. M equal plus 1 will be deviated upwards, for instance. M equal minus 1 will be deviated downwards, and m equal 0 will go straight. So I have three possibilities, and what I expect compared to the Stern-Gerlach experiment is to have three deviations, three spots, and those three spots will be associated to now the value of the angular momentum of the magnetic dipole associated to the proton. Okay? And I need to do the experiment and measure what I have. And the result that was published in 1933 was a great surprise. It's not exactly the value that it's very different from the value that was predicted from this very simple model, where I only change the value of the mass, and then instead of getting the Bohr magneton for the electron, I now have the Bohr magneton for the proton, but there is a geomagnetic factor which is somehow 2.5. And that's a big surprise somehow. Okay? I do not have the expected value. And today, the value was a little bit different, is a little bit different with the one obtained by Stern at that time. But again, it's the order of magnitude. Stern was only wrong by something like 10% with the means of the experiment. And let me remind you, he had to measure the deviation, which was something like 2,000 times smaller than the one of the Stern-Gerlach experiment. And this is the value of the magnetic dipole of the proton, which are very well tabulated now, very well known. Okay? That's fantastic when you compare the means of the experimental means at that stage. Then he said, okay, I want to do it. Now let's compare to something different. And something different, it's a magnetic moment of deuteron. Deuteron, it's like deuterium, you have hydrogen. And now I take a molecule which consists of one hydrogen atom plus one deuterium atom, okay? And then you have one proton plus one electron. And you want to reproduce the things. What do you expect? The neutron does, in Dirac theory, the neutron has no charge. And if it has no charge, it cannot have a spin. So basically, you would expect to get the same results, either for this system and for the other one. And that's somehow perhaps what he wanted to test. And deuterium molecules were discovered in the early 30s by a chemist in Harvard, Harald Urey. And so we got some of the deuterium and could try the experiment. But then, unfortunately, couldn't do the experiment in Hamburg because in 13th of January 1933, Hitler was appointed Reich Chancellor. Immediately, there was a promulgation of law against Jewish people. Otto Stern was Jewish, and somehow at that point, there is a long story about that, but he decided to quit Germany, and he found refuge at the Carnegie Institute of Technology in Pittsburgh. But then he restarted completely to reconstruct a lab. It was a great effort Somehow he didn't have all the support that he got in Germany, but now hopefully he got it. And together with his student, Immanuel Echtermann, he was able to realize the experiment. And that was again another surprise. And the surprise was that he found that the magnetic dipole of the deuteron was different from the one that was observed, that was measured for the hydrogen. That's really remarkable. So if I come back here, this is what I have here for the proton. If I take now the deuteron, I had one neutron in the nuclei. I found a value which is very, very different. Here it's -1/2, the Bohr magneton, and now it's 0.5 times 1, even a positive value compared to the other one. And that's also not possible to explain. The difference, it's a new surprise, as I mentioned. In Dirac's theory, you do not expect that adding something, a particle in the nuclei that has no charge, will modify the spin. So what's the reason for that? And that was a mystery until we understood, or it was then understood a few years afterwards, that somehow the proton and the neutrons are not single particles, elementary particles like the electron. There is, as you know, quarks in that. And it is the structure of the quarks inside this particle that provide these different values of the magnetic dipole. And today we know, of course, the magnetic moment of the neutron, and it's a little bit different than the one that was previously measured, but again, it's significantly different than the one of the proton. So to conclude this part, we have now nuclei, all nuclei that have non-zero nuclear spin will have a magnetic moment. The proton, the neutron, as I mentioned, are spin 1/2, and they have magnetic moment associated that can be measured. And I will show you how they can be measured much more accurately than the experiment that Stern realized. That's the purpose of magnetic resonance experiments. And if I take fluorine also, depending on the isotope that you consider, you will fluorine, for instance, isotope 19, will have a spin 1/2 too. Now, in the case of diamond, we will find 3 nuclei that are important. First, carbon. Carbon, if I take carbon, the natural abundancy of carbon is carbon-12, mostly, 99%, and 1% of carbon-13. Carbon-12 has no nuclear spin. So no nuclear spin associated to that. Carbon-13, you add 1 electron, then it has a nuclear spin 1/2. And this is found with 1%, and we will see why it matters for the NV centers, this abundancy of carbon-13. If I take another impurity, which is somehow intrinsic to the NV centers, it's a nitrogen atom that will be added as an impurity in the diamond lattice. Nitrogen can occur in 2 isotopes, either nitrogen-14. This is a spin 1 system, and the experiment will try to show you on Thursday will be related to the nuclear spin 1 to this isotope nitrogen-14. But you also can find nitrogen-15 with a very small abundance, below 1%, which is then associated to a spin 1/2. And if you control now the isotope that you introduce in the diamond to create the NV centers, you can use either natural abundancy, that you will get nitrogen-14 nuclear spin, or you can also use purified gas or purified systems, and then you will have, for instance, nitrogen-15, and then nuclear spin 1/2. Okay, this is important to remind for the following. Okay? But for all these nuclear spin, the nuclear magnetic moments are about 1,000 times smaller than the one of the electromagnetic moments, and I can rewrite them as this gyromagnetic ratio, gamma bar, to see that there's no simple theory explaining the value. For the case of the electron, we found that J is equal to 2, with a difference that can be measured with a remarkable accuracy. In that case, basically, it's a parameter given by nature that gave you the different values of these parameters, and that can change a lot depending on the element you consider and the isotope you consider. Okay, and there's no rule. And then you go to any formula, like given, for instance, by Brucker, and you will find all the isotopes. For instance, fluorine 19 is commonly used in chemistry for labeling and doing some NMR experiments in chemistry. Okay? To conclude that, I will introduce something that we might need for the following of the lecture dedicated to magnetic resonance, is a little, how can we get a representation of the spin 1/2, of the state associated to a spin 1/2. So we will represent the spin 1/2 state by what's called the block vector. And the block vector is simply a geometrical representation of the quantum state that we can write in this two-dimensional Hilbert space associated to the basis plus minus. Okay? So if I take the state psi as C plus 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 C minus minus, I can rewrite them as modulus C plus exponential E phi plus plus C minus modulus exponential E phi minus minus. And these, of course, the state is normalized, telling me that these two components squared are equal to 1 when I add them. And I can add these two values for C plus. Then I can rewrite them at cos theta over 2 and sine sinus theta over 2. Sine sinus theta over 2. So now if I neglect an overall phase, which is not important for the general description of the quantum state here, I can suppose that these two phase parameters, phi plus and phi minus, are equal to 0. And then I can rewrite them as 2 phi is equal to 2 for phi minus, and then I can rewrite the state in this way. Now I can factorize this factor here, and if factorize this factor here, then I got this value here of the expression of the state. And this is a general expression of the spin 1/2 state. Okay? Now if I look to that, it depends of two parameters, cos theta, a parameter theta, and a parameter phi, two angles. So then I can represent and use these two parameters, these two angle parameters, as the polar and azimuthal angle that will define the state onto a sphere. Okay? And so somehow this state also, it's a very simple exercise to show that this state is an eigenstate of the projection of the angular momentum projected onto a vector, unitary vector, r theta of phi. And this is what I will call, this vector will be called the block vector. Okay. This vector is a block vector. Okay, this is a block vector here. Okay, and so this block vector will represent the state. And I now have this picture, okay, here. And basically, this is, here I have the general definition of the state, okay, written in the basis plus minus. I can represent it as a vector onto a sphere with radius equal to unity. And this vector has important information. The projection on x, y, and z axis is simply the mean value, the average value of the magnetic dipole or the spin onto this axis. Okay? So somehow I can now, if I tell you I want to measure the projection, the average value of the projection of psi along, for instance, this axis, this is simply given geometrically by the projection here and the projection here. Okay? Just the component of this block vector onto the given axis you consider. And this tells you the value of the dipole. Okay? So then, if I apply, for instance, a magnetic field like that, I can have two kinds of magnetization associated to the magnetic dipole. I can have a longitudinal magnetization. This will be along the z-axis, or a transverse magnetization, which will be associated to projections of the magnetic dipole mu on the plane xy. And this is important to remind when we'll describe magnetic resonance. Okay? And this geometric representation is very useful because somehow it can be generalized to any two-state quantum system. And somehow the trick we will use with magnetic resonance is a general way to describe the qubit for quantum information, which is just the support of information using quantum mechanics resource. And the resource provided by the superposition, all superposition state created by a basis of plus minus state. Okay? And somehow, all the development of quantum technologies somehow relies on on the engineering of this qubit. And up to now, there's no one qubit which has been found much, much better than the other. There's many possibilities that have been implanted, that have been explored for those systems. So somehow how you can isolate a two-qubit, a two-state system. So you can rely on nature. And for instance, this is then, for instance, you will use ions or atoms, and you will isolate, for instance, a two-level state, a two-level system in all the levels of an atom. And the most efficient system up to now has been Rydberg atoms, because those can couple very efficiently at long distance by the interaction, by the coupling through these giant atomic antennas they have by these very high quantum number. This is one possibility. And then you want also to use technological resources to create your qubit. And that can be done by superconducting systems, for instance. Superconducting system is fantastic, something really fantastic. You imagine it's a system condensed by matter. It embeds millions and billions of electrons. But somehow, at the end, all these electrons behave as only a two-level system. Okay? And you can remarkably control this system. That's a possibility. Something which is a little bit closer to what we described, is electronic spin, for instance, in silicon. Of course, silicon, basically, you will choose, for instance, silicon-28. Silicon-28 has no nuclear spin. That's the matrix. But then you will introduce some dopants, like phosphorus doping, like was done from the semiconductor industry. You know how to control the doping. And then this phosphorus doping somehow will be isolated spin within the silicon matrix. And then you play with this spin, and you try to couple them and to construct quantum devices using these impurities in that. And the great point is that you can, for instance, try to detect electrically the spin state of the phosphorus impurity in that. And that there has been very, very nice experiments realized along that. You can somehow use photons. Photons, for instance, a single photon using the polarization either vertical or horizontal will be also a two-level system. And you can code the information of that. The problem at the end is how you make, for instance, two photon couple to each other. That's very difficult at the moment. We have no way to do that. We can do it a posteriori, but we do not have gates. For instance, it's not possible to construct a physical gate based directly on the interaction of two photons in a nonlinear medium, with only one photon interacting with another photon. That's not possible yet. Maybe in a few years that will happen, and then, of course, that will be a great step forward for all this technology, because the great advantage at photons is that you can propagate them and for long, long distance, and atoms or that. Of course, there are NV centers. We will speak a little bit about that. NV centers have been quite successful to get some dipole-dipole interaction, for instance. But then you need to put the two NV centers very close to each other. And this is, up to now, a great challenge if you want to extend the number of qubits based on NV centers that can be coupled to each other. Okay, and let me recommend this book. It's also maybe written by a French guy, Olivier Ezrati, and you can download it for free on the internet. It's 1,500 pages about all you might know, you might want to know on quantum technologies, and it's really like there's somehow too much of information to my point of view, but somehow he do that, and there's a very good, other people are doing that, but it's a very good survey. He published that from year to year, and it's a very good survey about all the things that have been described, and it's quite clever about separating real advances, real step forwards to some buzz that companies have been promote or launch to get more funding. So it's quite nice. But nevertheless, it's interesting. So somehow, keep in mind also that all the things that we're going to describe somehow can be easily transferred to other systems using the fact that a qubit is just somehow equivalent to a spin 1/2 in a magnetic field. I think I finished the lecture plan, what I planned to say this morning. This afternoon, we're going to speak about how we can play with this spin, and that's the wonders of magnetic resonance. And we will remind you a little bit of calculation. It's a little bit, not yet the NV centers, but all that will be very helpful for us in the following day, tomorrow and the other days. So, and we will look to that. I don't know. So let's stop at this point for this morning. And if you have any questions or comment, I would be happy to try to answer. Just go ahead. So everything was very clear? I doubt. Okay, you might know. Yes, please. Yeah. So a system that works at room temperature is the NV center. And people have done work to build, for instance, a kind of 2-qubit gate based on the coupling with 2 NV centers. Okay, that was demonstrated somehow. But the problem with that, there's different problems. The problem is this is not a scalable system. You will find I will try to explain a little bit how you can control that through the implantation of, for instance, nitrogen molecules. And by chance, you will have 2 nitrogen close to each other, converted into NV centers. And those 2 NV centers are a distance between 10 nanometers from each other so that they couple to each other. And that works at room temperature. That's perfect. So you could imagine now if I would be able to construct an array of NV centers like that, then I would be possible, I will have those kind of systems. And that would work at room temperature. The problem with that is that unfortunately we are not able to do that. The conversion rate, the yield of creating an NV centers remains a few %. So it's not possible to have those kind of system in a scalable way. So you will find a pair of coupled NV centers, I will show you, but you cannot scale it. Yes, but it's a good point. But again, it's a little bit the kind of limitation. So somehow, the thing that works at room temperature, but somehow also cool down, it's these systems. If you take, for instance, Rydberg atoms, with Rydberg atoms, you will have, atoms in vacuum, and they are cooled down by laser. So you do not rely on huge cryogenic systems like the one that is required for a superconducting qubit or the electron spin in silicon. The what? How it is measured now? He measured it by the... So he did that experiment and basically was able to detect tiny, tiny splitting of the line, differences of hydrogen molecule arriving here or here, deviated upwards or downwards. And from that, he could measure, knowing the magnetic field gradient, like in the Stern-Gerlach experiment, he could measure the magnetic dipole. But somehow, what was interesting is that this was, as you have to measure this very, very tiny difference, it was not a very accurate measurement. So that's why this value, you only have two numbers. And the good way to measure it, and I will show that, is using magnetic resonance. And somehow it's said that Rabi was a kind of postdoc or visitor in Stern Lab, and at that time he understood that. He understood that there was a clever way to measure the resonance about that, and that's what he implemented when he came back in the US, in Columbia. So we'll see how this can be measured much more efficiently using magnetic resonance.
In slide 17, you had mentioned that the energy difference term is responsible for diamagnetism. Could you elaborate?
Oh, that's a little bit far. Yeah, this one. This one, you see, it's something that couples to B square and depends on X and Y. And now, if you take, for instance, a hydrogen atom into this B square, and you go, for instance, to L equals 0 state, so the ground state. So the ground state will have, this value will not be equal to 0 on average. So this will be 0, okay, because LZ is equal to, the average value of LZ will be 0, but this won't be 0. So it means that in the ground state, the electron behaves in a way that it can produce a magnetic dipole which is proportional to B square. But this is much weaker than this value which is proportional to B. So somehow this induces what is called diamagnetism. So and you see there is also a difference. So this one will be associated to a value which is to a magnetization which is in the opposite direction of the magnetic field. Okay, if you do the computation at the end. Okay, so but basically it's proportional to B. This is responsible for the diamagnetism susceptibility. I don't know if there are any other questions. Okay, so I hope it reminded you some basic things in quantum mechanics, but again, this will be somehow useful for the following. And again, this afternoon, it's not really on the NV centers, but it's a general technique. We'll see basic how magnetic resonance somehow is implemented, what it is. It's a reminder also. I'm sure that many of you already have lectures on this topic. And then again, we'll see somehow how this idea will be somehow introduced with the specificity of the NV centers. Okay? Thank you. And so we meet in the afternoon.